Welcome back to episode 2 of this virtual field lab series where we're searching for hope on our warming planet. I'm Drew.
And I'm Zaina, and we're both atmospheric chemistry students here at the University of Washington. In the first episode, we saw that humans are capable of having a huge impact on the composition of our atmosphere. That could be a huge impact in a positive or a negative way.
In this episode, we're going to look at another huge source of pollution that impacts our atmosphere, our transportation system. We're going to look at the impact that driving all those cars has on the composition of the atmosphere. We're also going to look for more hope for the future in data pulled from ice cores from Greenland.
The transportation system is responsible for about 30% of greenhouse gas emissions produced by the United States. The cars, SUVs, and small trucks that we drive, they're responsible for more than half of that 30% generated by the entire sector. To stay focused, we're going to narrow things down to just the impact that our cars have on the atmosphere.
Let's write this investigation question down in your notebook. How much impact can transportation-focused environmental laws have on our atmosphere?
Let's start by making a data table in your notebook. We can fill in the first column with the number of cars on the road in the United States since the year 1900. I asked AI to compile data from several different sources, and this graph shows a pretty good estimate of the total number of registered cars on the road each year between 1900 and 2020.
Pause the video and do your best to estimate the number of cars on the road at the start of each decade. You can record your estimates in millions of cars. When you're finished, hit play again, and we'll look at the impact that all those cars have had on our atmosphere and the air we breathe. Welcome back. Here are my estimates for the number of cars in each decade. Our numbers might be a little bit different, but hopefully we're in the same ballpark. Most people know that burning fossil fuels like gasoline produces a lot of carbon dioxide, but there's also some other pollutants that get released. Some of these pollutants are different combinations of nitrogen-containing compounds. When these nitrogen pollutants are released from cars, they mix in the atmosphere with oxygen, and many get converted into NO3, nitrate ions. In this episode, we want to analyze how nitrate pollution in the atmosphere has changed as we've added almost 300 million cars to US roads. Let's add a column to our data table to record the amount of nitrate in the atmosphere.
If we look at the flow of the atmosphere, you can see that much of the pollution generated in the United States gets blown by trade winds towards Greenland. When we drill down into the Greenland ice sheet, we can pull up ice cores that contain a record of the pollution coming from the United States over the past few centuries. If we want to go back and sample the atmosphere from 1900, the time in history when we were moving from horses to cars as our main mode of transportation, we'll need to drill down hundreds of meters into the Greenland ice sheet. Lucky for us, the engineers at the University of Wisconsin and at the National Science Foundation Ice Drilling Program have designed drills that can drill these ice cores in Greenland and bring those cores back to our lab for analysis. Ice core samples are taken from Greenland and transported back to the U.S. Ice Core facility in Denver, Colorado. There, they carefully date the ice using several different methods and then ship samples that match the time periods we want to study to us here at the University of Washington. Once here, we then melt a small sample from each time period and inject the melted water into an ion chromatograph. An ion chromatograph can't tell us directly how many nitrite ions are trapped in the ice, but it can tell us how the concentration of our sample compares to a known standard. So if we want to test our ice samples to find out if the nitrate concentration in the atmosphere has changed over the past 120 years, we'll first need to construct a calibration graph by injecting some samples with known nitrate concentrations into our ion chromatograph. This is called generating a calibration curve.
Let me talk you through the first calibration sample. We'll start by injecting a sample of water with a known concentration of nitrate into the ion chromatograph. The first sample that I'm injecting contains 150 parts per billion of nitrate ions. The IC will generate a curve or a peak when the nitrate ions hit the sensor.
The higher the concentration of nitrate ions, the bigger the peak. The area under the curve is what we're interested in. The computer will do some calculus for us to give us an estimate of the area under the curve. This is the number that we'll use for our calibration graph.
For this first known sample containing 150 parts per billion of nitrate, the IC generated a peak with an area of 0.43 microsiemens minutes. Let's make a data table to record our calibration numbers and add these first two data points to the table. Let's collect calibration data for 3 more known values of nitrate. The second known calibration sample will contain a known amount of 290 parts per billion nitrate. We'll inject it into the IC. We'll let the IC calculate the area under the curve. Let's add the area data for this second point to our calibration data table. The third sample we inject will contain 440 parts per billion nitrate. The fourth sample we inject will contain 580 ppb nitrate. The last sample we inject will contain 740 ppb nitrate. Remember, the goal is to find out if the level of nitrate in the atmosphere has changed since the start of the car era of transportation, around 1900. Now, we have 5 calibrated data points for different nitrate levels. What we need is a tool that will allow us to estimate nitrate at any level, even if they're outside of the range of the calibration. To create this mathematical tool, we can graph the calibration data and find the equation of the best fit line using a standard y equals mx plus b format. Let's pause for a minute and use the calibration data to build a calibration graph. After making the graph, find the y equals mx plus b equation of a best fit straight line drawn through the data. Before you hit play again, try to rearrange the y equals mx plus b equation to solve for x, or the parts per billion of nitrate. The rearranged equation will be the mathematical model we'll use to calculate any concentration of nitrate based on any area generated by the melted ice samples we put into the ion chromatograph. Welcome back. Let's see how our calibration curve calculations compare. Here are my calibration data and best fit line. I made sure to anchor my line at 0, 0 for this graph, since I know that 0 parts per billion of nitrate will definitely produce an area of 0. We will need to find the rise and run to calculate the slope. You can pick any spot on the line to find the rise and run. I chose to draw my slope triangle at the 700 ppb nitrate level. I calculate a rise of 2.25 microsiemens minutes and a run of 700 ppb. The slope is calculated as rise over run, which when I divide gives me a slope of 0.0032 with units of microsiemens minute per parts per billion of nitrate. Now we can drop the slope into our y equals mx plus b equation. Y is the area on the IC, m is our slope of 0.0032, x is the concentration of nitrate, and the y-intercept is set to 0. If we want to isolate x, or the nitrate concentration, we just divide both sides by our slope. When we do that, I get the final form of our nitrate calculation as this. We'll just take the area we measure, divide by the slope, and that should give us the concentration of nitrate in the melted ice sample. Now we have ice samples from Greenland, an ion chromatograph, and a mathematical tool. Together, these three things should be able to tell us how nitrate in the atmosphere has changed as we added millions of gasoline-burning cars to our roads. In our lab, we take each sample of ice, melt it in a closed environment so that it can't get contaminated, and inject it into the ion chromatograph, just like we did with the calibration samples. Here's our first sample from about 1900. The IC produced a curve with an area of 0.198 microsiemens seconds. Let's plug this into our nitrate formula and calculate the level of nitrate in parts per billion. If I take our area of 0.198 and divide it by our slope of 0.0032, I get a nitrate concentration in the 1900 ice of about 62 parts per billion. Let's do one more sample together. Here's the ice deposited in 1910. This sample produced a slightly larger area under the curve of 0.208 microsiemens seconds. Let's divide the 0.208 area by our slope of 0.0032. I calculate the concentration of nitrate for the 1910 ice sample to be about 65 parts per billion.
Drew and I put all of the other melt samples through the IC, and here are the areas we got. Pause the video and use your nitrate formula to calculate the nitrate level at the start of each decade. When you're finished, hit play again, and we can compare answers. Welcome back. That was a lot of calculating. Here are the nitrate levels we calculated. Our answers should be all pretty close. I think data always tell a better story when shown on a graph. Let's pause the video again and transfer all of your car and nitrate data to the graph. Remember to include best fit trend lines for each set of data. Once you've finished with your graph, do a little analysis by writing down 2 things you notice and 1 thing you wonder. When you're finished with graphing and analyzing, hit play again, and we'll have Becky Alexander, an atmospheric chemistry professor from the University of Washington, come back to see what she thinks of our data.
Hi, I'm Becky Alexander, an atmospheric scientist at the University of Washington. Nice job with all of those calibrations, calculations, and graphing. When scientists like me see data like this, we get really excited because it isn't necessarily what we would have predicted. The best fit trend that I drew through this nitrate data looked something like this. In my mind, the data seemed to make sense until around 2010, when the nitrate levels seemed to begin dropping, even though the total number of cars is still going up. You may want to pause the video and brainstorm about things you think may be causing the nitrate levels to make an abrupt change in concentration. I came up with a lot of different hypotheses for things that might be impacting nitrate levels before I once again looked for a connection with major environmental legislation that may be causing this positive impact on the atmosphere. It turns out I needed to go all the way back to the Bipartisan Clean Air Act passed in the 1970s, the same Clean Air Act that we looked at in episode 1, and the same Clean Air Act that made such a positive impact on sulfate pollution and acid rain coming from coal-fired power plants. The original Clean Air Act of 1970 didn't specifically address nitrogen pollution coming from automobiles. However, in 1975, Congress passed a bipartisan amendment to the Clean Air Act that mandated all cars be fit with catalytic converters. Let's add a line to your graph showing when this legislation was passed. Catalytic converters dramatically reduce nitrogen pollution from car exhaust. Since 1975, it has been mandatory that all cars sold come with catalytic converters. Let's add another column of data to your table showing the number of cars on the road with catalytic converters. Before 1975, there would be 0. By 1980, just 5 years after the catalytic converter amendment passed, there were 43 million new cars on US roads outfitted with catalytic converters. By 1990, that number was up to 120 million, and by 2020, 250 million of the 280 million cars on US roads had catalytic converters. Let's add this new data to our graph. You can see how this story is a little different than the story of acid rain that we examined in episode 1. In episode 1, we saw how the Bipartisan Clean Air Act passed in 1970 began almost immediately to have a positive impact on the problem of sulfates and acid rain. It only took a decade for pollution control systems installed on our coal-fired power plants to start to have a positive impact. Within just 20 years, sulfate levels had dropped dramatically. The story of nitrate and nitrogen pollution is a little slower, but just as inspiring. In the case of catalytic converters, they were only required on new cars, so all of the older cars on the road continued to add NOx pollution and nitrogen pollution to the atmosphere. You can see by this graph that 10 years after the Clean Air Act was amended, almost half the cars on the road had catalytic converters. But that was not enough to move the nitrate needle. It wasn't until 30 years after catalytic converters were mandated that we finally saw evidence that nitrate pollution was falling. This is also a great time to talk about just how complicated the chemistry taking place in the atmosphere can get. It turns out that the reaction that removes nitrogen oxide compounds from the atmosphere happens faster when the levels of those nitrogen compounds are high. This means that as the levels of the nitrogen oxide compounds drop, the chemical reaction that helps remove them from the atmosphere slows down. To me, this is another example of a place we can find hope in this warming world. It's another example of bipartisan legislation that, once implemented, really helped to clean up our atmosphere. Now, nitrates in the atmosphere do have a lot of negative impacts, but they are not the driving factor behind our warming planet. The warming that we're all experiencing is being driven mainly by increasing levels of carbon dioxide. And here in the United States, we still haven't passed any significant legislation that would begin to decrease the rising levels that are building up in our atmosphere. With that said, I do see hope for our future and what is possible with transportation options that are now available. Electric cars provide an option that not only doesn't produce nitrate pollution, but also, if they are charged with inexpensive renewable energy sources like wind and solar, are only responsible for a small amount of carbon dioxide being added to the atmosphere over their lifetimes. Replacing 250 million gasoline-burning cars with electric vehicles is a big target, but it is an option that we could choose to pursue. If I add the number of electric cars on US roads to our graph, you can see where we as a country stand in our efforts to transition to a clean energy transportation system. Here are the number of electric cars on US roads in each decade. And here is what it looks like when we add this data to the graph. You can see that just like catalytic converters, the graph is just beginning to climb. To have a measurable impact on the climate-warming carbon dioxide, we will need to commit to transitioning as fast as possible. Catalytic converters were mandated, and it still took decades for the number of non-polluting cars on the road to have a measurable impact. I do find hope in the future for my kids, in the fact that we have the technology to move to a clean energy system that doesn't add carbon dioxide to the atmosphere. We just need to choose to implement that choice. So it's up to you and your generation. The evidence we've looked at in these first 2 episodes suggests that when one generation is bold enough to pass big bipartisan legislation, the next generation really benefits. Hopefully, in 25 years, you can look back and say that your generation was responsible for the Carbon Dioxide Clean Air Act of the new millennium that propelled the planet toward a renewable, sustainable future. Thanks for joining us for this episode, where we analyzed how we are benefiting today from bipartisan environmental laws passed by previous generations. Come back for episode 3, where we'll change gears and look at phytoplankton farts. Yes, I said phytoplankton farts that are coming from phytoplankton living in the North Atlantic Ocean as another sign of hope for the future.